Hello everyone and welcome back to another video. Today we'll be taking a look at another Project Euler question, and this one is question number 75, I believe, and it's basically about Pythagoras. And I'll just let you have a quick read of the question before I explain the solution. Okay, so the solution which I'll cover is definitely not the only way to do it, but it certainly is the most elegant way of doing it. This basically was inspired from 3 Blue 1 Brown. He's an amazing maths YouTuber, and definitely check out his videos on Pythagorean triples if you haven't seen it already. But we'll basically solve this in the following way. So first of all, when we read the question, we first identify that it'll be much more beneficial to generate all the triples first, and then decide for which lengths there's repeats, or there's exactly one integer sided length which can be formed, rather than doing it the other way around. So first going through all of the numbers and then seeing whether that can be made into a triple. So generating all the triples is definitely the way to go. So when I first solved this, I came up with a really inefficient way of generating the triples, and it was way too slow to be done all the way till 1.5 million. But then later on, a few months later, I watched a 3 Blue 1 Brown video, and that has inspired me. So basically, the way 3 Blue 1 Brown did it is he considered the Argand diagram. So if we basically consider any complex number, it can be represented as a plus bi. So it has its real part and it has the imaginary part as well. So and you might be thinking, well, how does this help us at all? How is this related to Pythagoras? But the link is actually really elegant. So we can also think of this as a vector. It has b units up and a units to the right. And now, one thing which we notice is that when we multiply complex numbers, it's kind of like vector addition. So the magnitude of the resulting vector, so this will be the resulting complex number if we multiply a plus bi by itself. And the reason for that is the magnitude will basically square, because imagine if you have any number and then you square it, you multiply by itself, so you square it. So that basically means that the magnitude of that would also square. So for example, the square root of 5, when you square that, it becomes 5, so the magnitude has squared. And it works exactly the same way with complex numbers. So maybe if we just call z, and if we define that to be a plus bi, then we can basically define z squared. The magnitude of that will be a squared plus b squared, the square of the magnitude of z. And the way we can just write this is we can just multiply z by itself, right? So a plus bi times a plus bi. And now, if you haven't seen complex numbers before, I should probably also mention that in this case, the reason why we have the imaginary axis is this axis is basically this is the real number line, so this varies between minus infinity and positive infinity. But then this axis varies between minus infinity times I, where I is the unit complex number. I is equal to the square root of minus 1. And it varies to positive infinity times I. So, which is why we plot it like this. And so the reason why I is defined like this is because we have no number which can square to give minus 1. So we define a new number called I, which can do that for us. So if we consider z squared, and then if we expand this out, we basically get the following. So the first term is a squared, then the next term is 2abi, and then the final term is bi squared, right? Okay. And now, if we remember from our definition of I squared is equal to negative 1. Therefore, by definition, this will be the answer of z squared. It will basically be a squared minus b squared plus 2abi. So this is basically the real part, and this is the imaginary part. So maybe let's just draw a new diagram. These diagrams are called Argand diagrams as well, for plotting real versus imaginary. So this particular number, its vertical component will be 2ab, and the horizontal will be a squared plus b squared. Since, remember, on the imaginary axis, we'll have a component of 2ab, and vertical, a squared minus b squared. Sorry, this looks like a plus. I should just make this a minus. Okay. And now, remember what we were saying earlier is that the magnitude of this vector is basically going to be a squared plus b squared, because the magnitude of this is the square of the magnitude of z. So then we basically have this resulting triangle. So let's just draw this a bit clearer. So we have a triangle with lengths a squared minus b squared, 2ab, and a squared plus b squared. And now the reason why this helps us so much is because, I'll just increase the thickness a bit. Yeah, so the reason why this helps us so much is because this resulting triangle which we have, it's basically going to be made up of 3 integer side lengths, right? So if we choose a and b to be any numbers, all of these side lengths will be integers. And that sounds an awful lot like Pythagoras, right? If we choose a and b to be any numbers, as long as all the side lengths are integers. So now, when we basically plug in different values for a and b, we notice something really, really fascinating. So when a equals 1 and b equals 2, sorry, when a equals 2 and b equals 1, since remember a has to be bigger than b, a squared minus b squared will be equal to 3, 2ab will be equal to 4, and a squared plus b squared will be equal to 5. So we've generated one triple, 3, 4, 5. And now, okay, that's nice. Maybe let's generate another one. So if we find a equals 3 and b equals 1, a squared minus b squared would be equal to 9 minus 1, so that's 8. 2ab is equal to 6, and a squared plus b squared would be equal to 10. Now we generated one more triple. Okay, that's pretty cool. Maybe let's try and make a and b different numbers apart from just 1 and something. So let's just choose some random things, like a equals 4, b equals 2. So a squared minus b squared, in this case, 16 minus 4, it's 12. And now 2ab, it's equal to 2 times, it's basically 16, and a squared plus b squared is equal to 20. Another triple. Okay, these all coincidentally happen to be multiples of the 3, 4, 5 triplet. Let me try and come up with one which isn't going to be a multiple of that. If we go a equals 4 and then b equals 1 maybe, I think that works. So in that case, a squared minus b squared is basically equal to 15. 2ab is equal to 8. And then a squared plus b squared is equal to 17. Again, this is actually a triplet. Remember, 17 squared is equal to 15 squared plus 8 squared. So what exactly is going on here? How have we generated so many triplets? Well, it makes sense that as a and b vary, we should be able to generate triplets because all of these are going to be integers, right? So these are all members of the positive integers, the set of positive integers. So it makes sense that we generate triplets like this, but then how are we sure that we generate every single Pythagorean triplet through this? The reason why is because if we vary a and b to be all numbers, then we'll pretty much get all pairs or combinations of 2 square numbers, which then add up to the third number. So basically it's exhaustive, right? So we'll be able to get every single triplet through this mechanism. So now let's just formalize the algorithm which we used. So we basically choose a and b to be any 2 positive integers, and such that a is greater than b. And then we basically have 3 side lengths. If we define them to be capital A, capital B, capital C, in true Pythagorean format, like ABC, a squared plus b squared equals c squared. So this side length will be a squared minus b squared. This side length will be 2ab, and this will be a squared plus b squared. And now it turns out that a, b, c are a Pythagorean triple. So now we have a really nice, quick, elegant way of generating triplets. So let's go to the program, and now let's see how we're going to use this. So, this is the answer. Okay, so basically, we we're just initializing a few variables. We'll come back to that. But, excuse me, this is the heart of the code. So what we do here is we make sure that A is greater than B first of all, and they both vary from 1 to 1000 in this case. We can make 1000 any number we want, but we'll just we just have an upper limit on what exactly we want these numbers to be. And then the triplet which we have is a squared minus b squared, 2ab, and a squared plus b squared, as I just explained on the whiteboard. And now, basically, the next thing which we have to do is we define L to be the sum of all of these. So L is basically the lengths. So the integer length would just be the sum of the three individual components making up the triangle. And now, one thing which we noticed when generating the numbers was that we found lots of multiples, lots of integer multiples of triplets which we already had. So we got 6, 8, 10, and then we also got 12, 16, 20, I believe. So if it's if it's equal to 1, if the GCD of A and B is equal to 1, i.e. the A and B are both co-prime, they have no shared factors, then we add it to the set of originals. And now the originals is basically just all the original triplets, if you like. So the ones which cannot be multiplied, like the ones which aren't scalar multiples of each other. And the reason why this originals thing helped us is since this method, it doesn't actually account for all the possible scalings which we can have. So if we have the originals, then we can scale it in all the ways in which we want. This method will give us some of the scalings, but it won't give us all of them. But then through this original, we can ensure that we get all of them. And then what we do is for each of the originals, we basically scale it by some sort of multiple. And then whatever that multiple is, we increment that to lengths. Okay, so that's basically that. And then after we're done with that, we just go through all of the different lengths. If the number of ways in which we can get to that number is just 1, then we increment our count. Finally, we just print out our count. And we basically continue this all the way till the end, and would find n to be 1.5 million, just as required in the question. And now if we basically run this code, we can see that the answer is 161,667, and executes very quickly as well. So yeah, that's pretty much it for this particular question. I really hope you enjoyed watching this video. It was definitely a very fun question to do, and hopefully you learned something new, maybe about complex numbers, maybe about Pythagorean triples, maybe combining the two. And I hope to see you in another video next time. Thank you very much for watching. Bye.